Hello friends, welcome to the Thermodynamics of Polymeric System Phase 3 under the edges of Polymer Process Engineering. In the last lecture, we have discussed about the enthalpy entropy calculation for various polymeric system. We discussed about the phase behavior of polymeric system, then fugacity, activity, equilibrium conditions, theories, various theories like Flory-Huggins theories in the thermodynamic system. In this particular segment, we are going to discuss about the activity coefficient models. We will discuss about the Flory-Huggins theory. Then we will discuss Hansen solubility parameters, correlation of various solvent activities because solvent play a very vital role in shaping the polymers to the useful product. Then we will discuss about the group contribution model and equation of state models. Now the first is the activity coefficient model. Now, in practice, the original Flory-Huggins theory, which is not accurate enough for a quantitative representation of polymer solvent phase equilibria. Now, to improve this situation, a concentration dependent Xi parameter can be introduced. Now, for this, the Flory-Huggins, they proposed the things, and for a solution of a polydispersed polymer with M polymer component in one solvent, the Flory-Huggins expression for the Gibbs energy of the mixing per mole of lattice site, this can be written as delta G for mixing over RT is equal to psi S ln plus summation I psi I Ri inverse ln psi I plus psi S psi P G SP, and G SP is equal to is a function of temperature and psi P. Now the sum is only over the polymer component psi I is the segment fraction of polymer component I. So this can be psi P is equal to summation of I is the summation from I is equal to 1 to M, psi I is equal to 1 minus psi S. Now to avoid any kind of a confusion with the polymer solvent interaction parameter of the symbol, GSP is used instead of Xi, which is independent of concentration. Now this GSP is equal to A plus B over T plus Ct plus D psi P plus E psi P square. Now GSP is equal to A plus B plus C over T 1 minus D psi P. Now GSP is equal to A plus B T plus C ln T over 1 minus D psi P. Now this ln excess gamma S is equal to ln psi S plus 1 minus 1 over Rn psi P plus GSP minus psi S del GSP over del psi P square. Now this ln xi gamma I is equal to ln psi I plus 1 minus Ri psi P over R and minus Ri psi S plus Ri G psi P psi I square. Now Rn is equal to Ni Ri over I is equal to 1 M summation from I is equal to 1 to M Ni, where Rn is number average chain length of polymer. Now Hansen solubility parameter, according to the regular solution theory of Hildebrand, the Xi parameter can be approximated by is Vs over RT del S delta S minus delta P square, where Vs is the molar volume of the solvent, delta S is the solubility parameter of solvent, and delta P is the solubility parameter of polymer. Now, this Hansen suggested the refining of the solubility parameter theory and introduction of the contribution from the dispersive interaction D and the polar interaction P and hydrogen bond formation, that is Hb. So, this can be represented as Vs over RT delta S D delta P square plus delta S S HB and xi is equal to alpha Vs RT delta S minus delta P plus 0.25 delta S minus delta P plus 0.25 delta S HB minus delta P HB. Alpha is equal to 0.6. Now, since the middle of 1990s, the model for the activity coefficient have been put forth that combine the Flory-Huggins kind of expression for the combinational entropy of mixing and the segment-based local composition model to take into account the contribution from energetic interaction. In 1993, Chen they put up a correlative model of combined non-random two-liquid NRTL theory with the Flory-Huggins expression for the entropy change. Now, correlation of solvent activity. Now, in place of NRTL theory, Pedrosa, he suggested uniquac theory in 2004. Now, using the database of 70 low pressure VLE system, they examined the different combinations of contributions and residual contributions. Now, as an illustration, we will provide the expression for the activity coefficient of the solvent for a model that combines the segment based NRTL residual term along with the P free volume term, and the contributions and the free contributions, they are combined in the P-free volume combinatorial term. The activity coefficient of the solvent is given by ln gamma S is equal to ln gamma S plus ln S residual. Now, this combinatorial free volume term is given by ln gamma S combinatorial free volume is equal to ln phi S, this viscosity, over plus 1 minus phi S excess. Now, the free volume fraction, this psi Fv is calculated as xi vi Fv over summation j xj VIFV. The free volume of the component is usually defined by VIFV is equal to minus VI VDW, where this Vi is the molar volume of the liquid component I, and this Vi VDW is the hardcore volume or van der Waals volume of this particular segment. Now, P correction factor, which can be calculated as P is equal to 1 minus Vs over Vp. So, the residual term can be given as ln gamma S residual Qs xp square tau Ps R over xs plus xp Gps square plus tau sp gsp square over xp plus xs gsp. tau e to the power aij rt, and gi is equal to e to the power minus alpha tau ij, where ASP and APS are adjustable interaction parameter, and A is the NRTL, non-random parameter, which is fixed as by the Pedrosa at 0.4. Now, so Xi is equal to Xi Qi over summation j xj qj, and Qi is equal to Ri 1 minus 2 alpha 1 minus 1 upon Ri, where Xi is the effective mole fraction of the segment of species I, and Qi is the effective segment number of species I. Rs is equal to 1 and Rp is equal to R. Now, group contributions method, this can be used to forecast the thermodynamic properties. Now, these models divide molecules into functional groups. Now, instead of considering the interaction between the molecules, group contribution model for activity coefficient take into account the interaction between the functional groups. So, there are significant few functional groups, then there are potential molecules that could be made up of these groups. A smaller number of group interaction parameter can be used to characterize a large number of system. The regression of experimental data is how these group interactions were discovered. So, the group contribution approaches, they are thus entirely predictive. The group contribution approach for activity coefficient are typically less accurate than the correlative models, since specify this particular specifics of the molecule structure are not taken into account. So, Oshii they proposed the writing of a solvent activity coefficient for the polymer solvent system, and they are the sum of the terms like ln s ln plus ln gamma s for viscosity plus ln s for the residual. The combinatorial contribution of this gamma accounts for the difference in the size and the shape of the molecules. The free volume contribution of gamma then for the viscosity accounts for change in the free volume due to mixing, and that is caused by the large difference between the free volume of pure solvent and polymers. So, the residual contribution accounts for energy interaction, and some of the workers they use this Oshii to represent the combinatorial contribution, a modified version of Flory-Huggins equation, which is also utilized in the UNIFAC group contribution model. The residual contribution also uses the UNIFAC model's corresponding formula. The UNIFAC model residual contribution with the temperature dependent interaction parameters serves as a representation of the residual contribution. Now, the liquid molar volume, this requires for calculating the free volume of a component. This can be determined experimentally by using the Tate equation or by the Albro group contribution approach. So, the molar hardcore is calculated from the pure component hardcore molar volume using the linear mixing rule. Now, what is this linear mixing rule? This one can be represented mathematically like this: Xi C is equal to I Xi Ci. Now, these same type of mixing rule is used for a number of approaches. Now, the group contribution formula in these equations, they are used to determine the pure component hardcore volume and the C parameter. Now, here this can be represented like this: 21.9662 summation of m Vm I Rm, and Ci is equal to summation of n V n Ct naught n plus Ct n 1 over T minus 1 over T naught is equal to this summation n Rn over summation mRm Cn naught. Now here the Vi is the number of groups of a type in n molecules I, T naught is the reference temperature, Rn is the normalized van der Waals volume of the group n used in the UNIFAC model. Now the attraction term, sometimes E eta is related to the UNIFAC model and Z is the lattice coordination number chosen to be equal to 10 and Qi, the surface area of the molecule I, which is given by this attraction term is equal to summation I half Z Qi xi plus summation j theta j e to the power delta minus delta over RT delta epsilon ji over summation k theta k exponential minus delta over RT minus 3R ln 1 by 3 minus 1 summation I xi summation n Vn Ct n. Now Qi, this is can be represented as Vn Qn. Qn is the normalized van der Waals surface of group n as in the UNIFAC, and the interaction energy parameter, this epsilon ji and epsilon delta epsilon ji is given by the equations. Epsilon over nu and delta epsilon ij is equal to epsilon ij minus ii. Now where this epsilon naught ji is given by ji and j epsilon nm, and epsilon nm is equal to minus epsilon nn epsilon mm to the power half plus delta epsilon nm. These expression the volume fraction psi of the molecule and the segment fraction theta I of the molecule I. Now the segment fraction in the theta n in the molecule, they are defined by the equation phi I is equal to xi Vi star over j xj Vj, the reference, then theta I is equal to x I qi over summation j xi qj, then theta n I is equal to V n I q n over summation m v m I into q m. The resulting expression for the free volume contribution and the residual contribution in the activity coefficient is given by ln gamma I is equal to 3 1 plus Ci ln 1 by 3 minus 1 over minus Ci ln Vi over V, and ln gamma I residual is equal to 1 over 2 ZQi 1 over RT epsilon minus epsilon II Vi plus 1 minus ln summation j theta j e to the power minus delta epsilon j I over RT minus summation j theta j e to the power minus delta epsilon j I over RT over theta k e to the power minus delta epsilon k I over RT. This is summation. Now, this graph comprises or compares the experimentally determined solvent activity of the system for the polypropylene oxide benzene at 347.85 Kelvin at unified correlation. And this correlation's outcome is nearly perfect. And this particular graph illustrates the agreement between the prediction made by this group contribution Flory model for the homopolymer solvent system and experimental solvent activity coefficient at infinite dilution. Now, let us talk about the equation state model. The high pressure phase equilibria in system of polymeric system or solvent and supercritical gases, they are almost in all cases modeled using the equation of state. So, one of the first equation of state that was used to model the high pressure phase behavior of polymer solvent system was the Flory equation of state. And Peterson and Delmas, they showed the equation of state can be used to describe both LCST and UCST phase behavior. And some of the co-workers, they created the perturbed hard chain theory. It can be used to model the phase behavior of mixture for small and big molecules, including the polymer, across a wide range of pressure and temperature. Now, this can be seen as an advance over the method of Flory and co-worker. Now, basically there are two equation of state methods, the relatively simple, that is Sanchez-Locombe lattice fluid model, and statistical associated fluid theory, that is SAFT, which has now become one of the standard equation of state for the polymeric system. Now, Sanchez-Locombe lattice fluid theory, this theory, like the Flory-Huggins model, it is predicting the idea of a portion of solvent and polymer molecule to fill the lattice sites of a rigid lattice, although unoccupied lattice sites are also permitted. Now, the compressibility is also introduced by the pressure dependent relationship between the total number of lattice sites and number of unoccupied lattice sites. So, the resulting equation for the pure component is given by PV over T is equal to 1 over R minus 1 plus V ln 1 minus 1 V 1 over Vt, where P is the reduced pressure, this one, and this is the reduced volume, and this is the reduced temperature. Now, the reduced volume and the reduced pressure, and this can be defined as bar V is equal to V over V standard, which is equal to N naught plus Rn over Rn, and reduced pressure can be defined as P over this standard pressure. This is PV standard pressure epsilon, and this reduced temperature is defined as KT over T star. The parameters with this standard is called characteristics parameter, and the practice R of the number of segments per molecule, epsilon is the interaction energy parameter, and V star is the molar volume of the lattice site. They are used as the independent pure component parameter, and N is the number of moles of the component, and N naught is the number of moles of vacant lattice site. Now, for mixture of same equation of state is used, but the characteristics parameter R, epsilon star and V star are composition dependent. So, the new this give an overview of different mixing rule proposed in the literature and often used mixing rules. This can be given as R is equal to summation of Xi Ri, V star is given as psi I Vi, and epsilon star is given as summation of psi I psi j, roots of epsilon j, epsilon I at the standard condition, then epsilon j its standard condition, 1 minus k I j. Now, this kj is the adjustable binary interaction parameter which equals to 0 for I is equal to j. Now, the segment fraction of ji for the component psi is given by psi I is equal to xi ri over summation xi ri. Now, according to Nu, the correct expression for the fugacity coefficient of the model given by ln psi I is equal to minus ln z plus ri minus 2 1 over Vt minus ln 1 minus 1 over V plus z minus 1 over xjrj into nr over V star del V over del Ni Nj is not equal to Ni minus 1 over Vt into Nr over epsilon del epsilon star over del Ni. Nj is not equal to Ni. Now, the compressibility factor, because sometimes it is always required to assess the deviation from the ideal behavior, this can be given by PV over RT, that is reduced pressure, reduced volume and reduced temperature R. Now, in this particular figure, the Sanchez-Locambe equation of state is used to fit the data for to the experimental isothermal cloud point curves um, in the linear low density. Now, the PVT data and the data shown in this particular graph, they are simultaneously fitted to yield the polymer's pure component properties, and the equations that were resolved, they were those of Koch and Henderman described. The temperature, they had the linear relationship with the binary interaction parameters. So, dear friend, in this particular segment, we discussed the different model for the polymeric system, and we see that how these equation of state play a vital role in the predicting the thermodynamic behavior of polymeric system. We have been listed several references. You can utilize these references as per your need. Thank you very much.